Hello everyone. In this video, let us try to look into the remaining quality check parameters of the clock tree, which is latency and the clock tree power. So let's move to latency first. So in this case, the latency or the time required for the clock to reach from this point to this point. Let us try to calculate that value first. So it will be in let's say this is 1 RC. This is 2 RC. It is 3, 4, 5, 6, 7, 8, 9. So it's 9 RC constant values, or 9 RC constant. That is the time period that is required for the clock signal to reach from this point to this point. Or in that case, the time required for the clock to reach from this point to any of the clock endpoints, it's 9 RC. So latency is one such term on which we can always try to improve on that particular number. For example, in this case, the latency value is like 9 RC, but the question remains that can we get better than 9 RC? Can we get some value which is like 5 RC, so that we can get a less value of latency? So it's always an improvement that we can do on the latency, because latency in other terms can improve the clock tree power. So these two are interrelated. So there is always a scope of improvement for latency to a reasonable limit. Right now, the limit that will decide the value of latency is the transition. So in this case, the transition, if you look, it is very bad. It's worse than what it was at the input. So we can improve the value of latency in such a way, or for example, we can get this transition value not as worse as this one, but somewhere over here. So we can, if we are able to get a decent value of latency by a transition which is somewhat similar to input, then we can say that is the best possible latency that we can achieve. In this case, we see still a very huge scope of improvement, because the transition at the input and the transition at the output are way off. So in this case, if unless and until we are able to come up with a value of transition which says the latency, or which says the transition lies somewhere in the middle, or which is very close to the input signal, we can say that the latency is a very good number. But in this case, in the tree that we have built, the input transition and the transition that we receive at the clock endpoints are way off. This is very bad over here. So let's put a red cross over here, which says that the latency is we have a number with the latency, but we are not satisfied with that, because the transitions at the input and the transition at the clock endpoint are not exactly equal, or not close to equal. So let us try to put a red cross on latency. Next is the clock tree power. So clock tree power is again a function of latency and the transition of the signal. So the worse the transition, the more is the amount of clock tree power that is getting lost. So let me give you an analogy over here. So for example, we have a person who is running. For example, let us assume that this is a race course. The race is from point A to point B, and there is a person who is running from this point to this point without any breaks, because there is nothing, there are no buffers, there are no repeaters in between. So this person is running from this point and continuously running and reaches till this point without any breaks. So in that case, he loses a certain finite amount of energy, and he loses a massive amount of energy in that case. Other than there is one more case. Let's say if the person had been running from this point to this point, taken a break, had a cup of water, and then again ran from this point to this point, taken a break, had a cup of water, and so on, repeated over here, then the amount of energy that would have lost would have been less. But in this case, since the person is running from this point to this point continuously without any breaks, that results into huge amount of energy loss. Similarly, for clock signal, we have the clock signal that is running from this point to this point to all the other clock endpoints without any breaks. So in that case, a huge amount of energy is getting lost, and hence we see that the clock tree power clock tree power that is getting lost is humongous in this case. So in also if you see at the end you see a transition. If you see the signal of, if you see the signal has got this amount of transition, so what happens, this particular endpoint is again connected to a bunch of PMOS and NMOS over here. So during this particular transition period, both the PMOS and NMOS are turned on, and you have a huge amount of short circuit current that flows from VDD to ground. So this is again a bad for the circuit. If you have this amount of transition over here at the end point, that creates a lot of short circuit power dissipation, and hence clearly we see there are multiple reasons to comment that the clock tree power is a big is a big red cross over here. So let's try to put a big red cross for the clock tree power also. And the signal integrity and crosstalk, we will be, as we discussed in the previous video, we'll be talking more about signal integrity and crosstalk in the separate class of videos, because this particular thing requires more detail or the more comprehensive explanation of the concept. So let us try to keep this in the separate video, and let us not try to mix this with CTS. So if you look into this particular slide, we have a clock tree over here, and we have the, let's say, checklist over here. So the checklist says we are good with skew, we are not meeting pulse width, we are meeting duty cycle, but it's of but it doesn't add any value to the target that we want. So duty cycle is a red tick. We can comment on latency. So in this case, why we are not good on latency? The reason is because the transition at the input and the transition at the output are way off. We need transition should be at least very close to what we send at the input. So because of that, so the amount of allowable repeaters that we can add in this circuit, that depends upon the transition. So we'll be talking about repeaters and the buffering in the later sections of this slide. So transition is a big, so latency is a cross for us. Clock tree power, we said that the clock is continuously moving from this endpoint and to the other endpoints without any breaks. So and also the transition that you get at the output at this points are also very sharp, is not very sharp, and hence there is a huge amount of short circuit current that flows when you move from logic 0 to logic 1. So this is the status of our H tree. Now if you actually look into this circuit, if you actually look into all the in all these points, there is one common point which is present in all these checks, is the transition. We have talked about transition, and we have always blamed a transition for the failing of the remaining ones. So transition is one parameter that we need to see how do we bring it under control. Once we try to bring this thing under control, once we try to bring this thing similar to what we send at the input, lot of problems will get solved. Lot of this reds will turn to greens. So let us try to see a methodology, a way of how can we reduce the transition on the chip. So let us try to look into that, and that brings us to our next topic, which is clock tree buffering. So clock tree buffering, the term itself says we are going to buffer something. So buffering is a very common concept across VLSI world. So let us try to look into details of the buffering, of how do we do buffering, what are the number of buffers that is actually required. So let us try to do some quantitative analysis of the clock tree buffering. In this particular slide, I have taken a circuit from one of my own videos which I have been delivering under the section called VLSI Academy. So you might want to have a look into that particular VLSI Academy videos, so that you will understand from where this particular diagram is coming from. So over there, what we did was, we have taken a sample circuit. We have taken a small circuit over here with 8 flops and tried to implement that circuit on a chip. So okay, so we have taken an example where we had 2 clock ports. So one of the clock ports was driving was running 4 flops, which is this, the green one and the blue one, and the tree was built in an H shape, and in an H tree, using the H tree algorithm. So it again it divides this particular thing into 2 halves and moves at the center. Then it again moves from this particular point to the other halves, and then connects to the flip flop 1 and flip flop 2, and the green ones and the blue ones. Similarly, we did for clock 2 also. We have taken the wire from the clock 2 and did an H tree algorithm, and then connected the clock to flip flop 1, flip flop 2, FF1, FF2, the yellow ones. So this is what we did over there. You might want to have a look into the VLS Academy lectures. Now what we'll do is, for this particular section, for the buffering part, to analytically understand the buffering part, we'll take one section of the wire. We'll take one section of the chip, which is the clock part. So let us take the clock wire over here, and let us try to do some analysis or some analytical quantitative analysis on this particular wire, and try to come up with some number that is required for buffering. So at the end of this, so since I'm running out of time, let me try to briefly introduce you. So at the end of this particular analysis, we will come to know the amount of buffer that will be required to control the transition of the clock signal, which is moving from this point to this clock endpoints. So what is the amount of buffers will be required? And the second thing will be coming up is how many at what distance the buffer should be placed. So we will be coming up with all those things, and we'll be talking about the clock tree buffering section and the analytical analysis of the wire itself in the next video. Thank you.